symmetry in polar equations is difficult because points don't have unique representations. We could have a point that looks like it should be on the graph, but maybe it's not the coordinates that we would expect it to be. So let me give you the general rules, but know that sometimes it's not, I mean, it might still be symmetric, even though the rules don't show it because of the representation of that point. Okay, so let's first look at symmetry with respect to the polar axis, which is our x-axis. What that means is that if we have a point up here in quadrant 1, we want to have the same point if we went the same angle clockwise. So the point up here in quadrant 1 would have the coordinates r theta, if theta is that angle rotated counterclockwise. So now rotate the same angle, same quantity, negative theta, clockwise, and you now would have the point that would be represented with r negative theta. So to check symmetry around the polar axis, replace theta with negative theta, and if you end up getting the same r value for it, then we're going to have symmetry about the polar axis, about the x-axis. So just replace theta with negative theta and see if you get the same r value. Okay, now looking at the line theta equal pi over 2, which is our y-axis. If you have an angle theta here, which corresponds to the point r theta, we're trying to determine if there's symmetry. That means this point here should also be on the graph. So what would the representation of that point be? Well, that representation, you have to look at the angle theta and where the reference angle would be theta in quadrant 2. In quadrant 2, the angle corresponding to that angle theta would have reference angle theta right here, which means that the angle corresponding to this point could be this angle right here, which would be pi minus theta. Okay? So, to tell if it's symmetric about that line theta equal pi over 2, we're going to replace theta with pi minus theta and see if we get the same r value. Okay? So if it does, then the graph will be symmetric about the line theta equal pi over 2. Okay? So replace theta with pi minus theta. Okay, so now symmetry about the origin. That says if you have a point r theta on the graph, you should also have the point minus r minus theta on the graph. Well, not minus theta. You've got to understand what this symmetry about the origin would mean. This is the point on the graph. This point's also on the graph. So it's not going to be minus theta. Instead, if this is the angle theta, what would the angle be that corresponded to this? Well, that would be pi plus theta. So this would be the point. Same r, but pi plus theta. Or you could use the angle theta again, but now go the opposite direction through the pole and make it a negative r. So this point over here could have the coordinates either r theta plus pi or negative r theta. Okay? So be careful with symmetry about the origin, because you have to check first. Replace the r with a negative r and see if you get the same equation, because you see here that if r theta is on the graph and negative r theta is on the graph for every r and theta, then you will have symmetry about the origin. So now one thing to keep in mind here is that if two of these symmetries exist, all three of them are automatically going to be true. So any two of the symmetries implies the third one. So that makes it a little easier. You just have to find two of them that work and then know that it will pass all the tests. Okay, I want to graph this one. First thing I'm going to do is I'm going to check for symmetry about the polar axis. And to do that, I'm going to replace theta with negative theta. So my equation then is going to become r equals 3 sine of negative 2 theta. Put negative theta where the theta is. Well, the sine function is an odd function, so this is the same thing as negative 3 sine of 2 theta, which is not the same value. So we actually get a negative r when you replace theta with a negative theta. Now what this did just show me, though, is that when r theta was on the graph, r negative theta was also on the graph. What would that look like? If this is a point r theta, so here's the angle theta, and this is the distance r, negative theta would be coming the same amount here, but then go the negative r. So that would mean you would have a point over here. So what we just showed, we were trying to show symmetry around the polar axis, but what we just showed was we have symmetry around the line theta equal pi over 2. So if a point over here is on the graph, the point over here is also on the graph. So this is actually showing symmetry about theta equal pi over 2. So that is equivalent to looking at pi minus theta. So a couple different ways you can actually show symmetry about the y-axis, or the line theta equal pi over 2. Now another one I want to look at is symmetry about the origin. Okay. What I want to do there is I want to look at r and theta plus the pi. So I'm going to replace theta with theta plus pi. And so my equation then becomes r equals 3 sine of 2 times theta plus pi, which now I'm going to need one of my trig identities. This is sine of 2 theta plus 2 pi. Well, I don't even need a trig identity. I know anytime I have an angle and add 2 pi to it, because the period of sine is 2 pi, this is the same thing as 3 times sine of 2 theta. So I get the same exact thing for the r that my original equation was. So putting in theta plus pi results in the same exact r value. So this implies symmetry about the origin. Which now I've got symmetry about the line theta equal pi over 2, symmetry about the origin, and automatically then, so therefore, it's also going to be symmetric about the line, the polar axis, the x-axis. Okay, so sometimes it doesn't work out the way you want it to, and it's all because of the way coordinate, the representations are not unique. So just be willing to kind of be flexible with this. So now let's see what the graph is at. The nice thing about that, if I know I have symmetry about the x-axis and the y-axis, all I need to do is plot in the first quadrant. So let's put some values in quadrant 1. If theta is 0, I'm going to end up having the r value is 0, so I'd be right here. If theta is equal to pi over 6, then I'm going to have sine of pi over 3, which is 0.86, so it's going to be 2.4, which will be somewhere out here. The largest this will be when that angle is pi over 2, so it'll be at the value of pi over 4 for theta, and that's going to be at 3, so it's going to be out here. Let's see. It ends up, if you graph enough points here, you're going to get a petal of a flower, and because we have that symmetry about the origin, the x and y axis, you're going to have the same flower in each of the same petal in each of the quadrants. Okay, so that would be the graph, and you just check the symmetry, and that limits how much of it you actually have to graph to know what the graph of it's going to look like.